Good morning, everybody. Welcome to our session on next generation materials research. Materials research, in particular, the digitalization of materials research is one of the big questions that we have to deal with, particularly the digital mapping of production and processing is a necessity of high industrial importance. And to introduce to the session, I have prepared a few slides. If I could get those, please, then I can guide you through. Yes, here we are. Thank you very much. So we have the pleasure to hear today 4 speakers on subjects relevant to our topic. In particular, we have Gerhard Goldbeck with us, Executive Secretary of the Materials Modeling Council. We have Deputy Director of the Fraunhofer Institute for Mechanics of Materials, Chris Eberl, also involved in a German platform on materials digitalization. We have Giovanni Pizzi with us from the École Polytechnique Fédérale de Lausanne. He's an expert in theory and simulation of materials, and particularly also handling data. And Bernhard von Vacano, Global Head Scouting and Incubation from Advanced Materials and Systems Research at BASF company. So this is the speakers, and now what's the subject? Challenges in materials production and processing. This is a topic of wide scope for materials, the materials community, and it comes with very different types of questions. So from materials design, materials development perspective, we ask questions like how can we reduce time to market, how can we substitute critical commodities or critical components in our materials. From the production point of view, the questions are how can we vary processing parameters for higher manufacturing output or facilitate decision processes. Also, from the operations point of view, we need to have information about the material, for example, when it comes to decisions for maintenance or the discontinuation of a material. And these questions come with very different needs. Needs for tools, needs for access to data, which I've only put a few points up here. There is the need to visualize various processing steps in the materials development process. There is the need for quantification of specific outcomes and the impact of production decisions on component performance. And of course, the reliability of a component or the maintenance questions need to be forecast. And so there's a need for materials modeling underneath to interpret data. And with all these different aspects, we have identified strong demand for the data as such, and the extraction of information at critical steps. We cannot just focus on the production processes, but we actually have to look at the entire materials life cycle. We require cause-effect relationships and connecting the processes with the changes in material structure and corresponding changes in materials properties. And we need to be able to manage all this information. So this is a big chunk of questions. And if we go down into what does it actually require, then there's 4 main areas. There's one, the area for structuring data, integrating data into hubs. Then the second step is to implement data streams and workflows to get the data into the hubs and into the structure. Then, of course, there is the need to analyze the data, to work with the data, to apply the data to our questions, and last but not least, the product development aspect. And our speakers greatly cover this spectrum of questions. Gerhard Goldbeck will talk about structuring materials data based on a common language. So this is for points 1 and also with applications in analysis and application. Chris Eberl will talk about using the data more to enable business opportunities through data-driven materials models. Mr. Pizzi is bridging between the structuring of the data and the hubs and implementing data streams and workflows. And of course, from industrial perspective, Mr. von Vacano will talk about driving sustainability with digitalization of materials. So from this point on, I would then want to call first talk by Gerhard Goldbeck and would like to call for the next slides. Let me briefly introduce Gerhard Goldbeck. I've mentioned he's Executive Secretary, Materials Modeling Council, located in Cambridge, as you may see from the background of his screen. And with that, I hand over to you, Gerhard, please.
Thank you very much, Peter. And it's my pleasure to start this session, and if I could have the first slide. So my talk, as was mentioned, is on structuring materials data based on a common language. And this is a presentation also from the European Materials Modeling Council community. And the Materials Modeling Council was really started in 2014 as an informal association of stakeholders across the field of materials modeling and digitalization, received funding through a coordination and support action in 2016, and following that was established as a non-for-profit association in Belgium, the EMMC ASBL. One of the key goals of the EMMC is to facilitate integrated modeling and digitalization, and this is really what I want to talk about today and how this is supported. It's really in the context of industry requirements that we've already heard about, and even in some of the description of the section here, it's about the precise manipulation of the respective influences and how can modeling and the digitalization support that, support by, obviously predictive science, we'll hear more about that, by insights, supporting collaboration. The focus here is underpinning digitalization by a unique way of representing materials, processing, and the according devices. So the representation is really the common language that we should develop to support the field across the many different disciplines. As we see here, materials are the result of a collaboration which is really unique and extremely wide across many different fields and subdisciplines, and also very many different historical areas. So when we talk about a material today, It involves chemistry, it involves engineering, it involves characterization, toxicology in nanomaterials. Of course, we use also modeling and information sciences. So many different areas that have traditionally had their own languages need to come together in one combined and coherent effort to support the development of these advanced materials and processes that we're looking for. So as a result of that multitude of disciplines, there is currently a lack of a common representation system. But there's also, hopefully I can show you some good news, because we can go back to the foundational principles of material science to organize our data. So what are these? Well, as was already mentioned also by Peter Gumbsch, they are the processes, the structures, and the properties are really the three dimensions shown here. Also, the processes along the top, and along these different processes, we also then see or observe or model structure, and this is what we say is the multiscale nature of materials in both space and time. But anything that we know about materials is by observations, and also we derive knowledge from theories and from modeling. So along and across that, we then have a number of, say, properties that arise from characterization, modeling, simulation, and testing that lead to a number of data that are shown here in these sort of database silos. So this is how so properties are really all we know about the material, whether it's in its processes or in its multi-scale structure. And that allows us then to design the material and to design with the material. But that framework we'll come back to. Now I want to look at each of these dimensions, the processes, the multi-scale structure, and the properties. So I'm going to use here also a visualization or graphic that has been developed in one of the EMMC related projects, the Ontotrans project. And what we're seeing here is the process dimension. So what is a process? A process is really converting material objects into other materials objects. And along that line, we again see properties, because all we can say about the process and the material is, again, what we observe about them, maybe by sensors or by the way it has been built, and by characterization and testing. So these observations and leading to properties are the knowledge sources that lead to the data that allow us to talk about the process. So keep that in mind. Then the next one is that both for the process and for these materials objects, we are often interested in want to describe their parts. So process is made up of different temporal parts, and a material object is made up of spatial parts. So this is the typical multiscale nature of a material, from the cogwheel to its microstructure and to crystal lattices and atoms and so on. So all of these are important in the description, and we talk quite naturally about that. In analytical philosophy, this is called mereology, the science of parthoods, and so we can connect with that. Now, again, anything we can say, though, and we know and have as data about both the processes and these objects, is through some sort of observations. And here is one example. So we could, for example, consider a hardness measurement by an indentation process. So we have a sample that participates in that process in an instrument, and it eventually gives us a reading according to a certain agreed theory or formula. So that leaves us with a data point and gives us all of the data. Then we can aggregate to know about what we know about the world. So these are the principles on which the common language, or in more formal terms, the ontology that we're talking about, is built upon. And this is the European Materials and Modeling Ontology, which is really a common representation framework based on the material science principles and analytical philosophy. So you can look at any type of material as it arises and behaves as a process, and this is what we call the holistic perspective. You can look at its parts, or mereology, or in engineering, a system or system of systems. This is the reductionist perspective, and you can know about these and get data about any of these through the so-called perceptual perspective. This leads to properties and how they are determined, which is actually also in line with many ISO standards about properties. So by applying this framework, we can make a connection between a physical world and a digital representation, about which all of the material sciences then can agree, and we can build really on any type of system on that basis. This ontology has been developed originally within the European Materials Modelling Council, and is now also still governed by the European Materials Modelling Council governance framework. But it is also further developed and applied in a number of European projects that are shown here: SimDome, Marketplace BIM, the Ontotrans project that has applications from washing detergents to making steels and composites, and to a project just about to start, which is on the ontology-driven data documentation for industry commons, giving that timeline all the way to 2024 in terms of development. So I would like to acknowledge the MO co-authors, Emanuele Ghedini in particular from University of Bologna, Jesper Fries from SINTEF, and Adam Hashibon from Fraunhofer IWM, and also the funding of MO through these projects that I mentioned, and in particular the EMMC, CSA, and the Ontotrans project. Thank you very much.
Thank you, Gerhard. Nice overview on the European activities here. Thank you very much, Gerhard. Now, we have a few minutes for questions. We have divided the entire session such that direct questions to Gerhard Goldbeck can be raised now. More overarching questions can be raised again at the end of the 4 talks, or after the 4 talks, where we have another 15 minutes for questions which link in between. I see currently no questions available, so I'll give you another minute or two to at least give the technical chance to put something in. If not, then we can certainly first hear the talks and then have a broader discussion at the end of the session. So again, thank you, Gerhard, for the moment. And we come to our second talk. Chris Eberl, head of Fraunhofer Institute for Mechanics of Materials, also expert on data usage. Please, Chris.
Thank you, Peter. So let me start off. Making money with data is shown by Google, by Facebook, by all the big companies which you know all around. But nonetheless, the problem is, if we look at how much money you have to put into one data set, let's say people put hundreds of hours into one data set, and then how much it really costs. So Facebook, the data of one person costs about $200, yeah, but they put hundreds of hours of data in there. The question is if this really works for the professional world. And as far as we know, this is not true. And this is why I would like to introduce also the data we're dealing with. And but before I want to do that, I would like to just get back to you and say, okay, what are the materials data's potential? And there are two other speakers from Vacano and Pizzi, which will give you a little bit a different view on it. We look more on the applied science point of view on it, and very much on the reliability. And the reason why we do that is also that we always, like Peter said, we always have to take into account the full life cycle of a material. And all of that needs to go into something like a sustainable world. And von Vacano will show how kind of materials we can come up with to maybe do that. But on the other hand, we have a lot of materials we can already do things like that, like with steel or with aluminum. We can almost recycle everything of it. But it's very difficult and often very intensive in terms of energy and also in terms of money. Now, we know all about the climate change. We know about that we have resource scarcity with some of the materials coming up. And we also want to therefore go to something like a cradle-to-cradle kind of infrastructure where we really take the material which we get, process something out of it, use it, and then at the end refurbish it into a state where we can reuse it again in a new application. And only if we can really do that, that's a sustainable sustainability we can reach as a humankind. And thanks a lot to Gerhard again. So one of the reasons is why we believe that we can do that, even though it's very complicated, is that we start by structuring the data, by introducing metadata about all these things. We can enrich the physical objects with information which can be used later on to really reuse them in a proper way. Now, if I may introduce to you something which is very, let's say, concrete. On the right-hand side, on the lower right-hand side, you can see a bearing. A bearing is maybe a little bit boring, but if that fails in a wind turbine, the wind turbine fails. And then a ship has to travel out to offshore wind turbines, and it's extremely expensive. And as we know, I mean, our industry and also our energy industry is driven by how much money they can make out of these wind turbines. And most of these wind turbines often are owned by our retirement funds anyway. So it's all of us which are hanging on their lifetime. And therefore, we want to make them as long-living as possible. And we know that there is a high $100 million number out there, which these offshore wind turbines cost every year to maintain. And the reason is that they fail over time when they're loaded cyclically. And I want to bring you in rather deep into this problematic to give you an idea how we can put data into business models. So if we go to the next slide, we can see that normally materials have an intricate inner structure, and Gerhard already introduced that. This is the important thing. So with all the processing, what we do, we store the deformation into the materials, often if we look at metals at least, or we store specific hybrid materials like fiber composites or anything like that. So it's a specific inner structure which gives the materials properties, and that is controlled by my process. So if I look at the metal pieces, which you can see here, this is a 3D cube where we cut different orientations, and you look at these different ones, and you can see that the inner structure is an intricate 3D structure, which gives the strength to these materials. And to really understand and work with that, we have to see how we can really understand what happens inside if a damage occurs. So what you can see on the right-hand side, the gray ones, the gray images are secondary electron images from a scanning electron microscopy microscope. And what you can see is that you can see these cracks in C. You can see in A and B, you can see these little extrusions, we call them. So they are roughening at the surface when you have a cyclic loading on the part. And with time, this A and B becomes a crack. And we want to know how that happens, when that happens, how is it initiated, how does it grow? Because that determines the lifetime of that big machine in the end. Now, what you also can see, and this goes back to what Gerhard was explaining. On the one hand side, we want to semantically describe the left-hand state when it leaves let's say, the company and is brought out to sea. And then on the right-hand side, we want to know what is the state at the moment when I look at these materials at a specific point in time. And how to do that is very tedious. We have a survey for another company. We try to figure out how many data points are available on lifetime for high-strength steel. They are in crash structures in your cars. They are in these bearings anywhere. They're all over the place. There are 6,000 data points worldwide, which you can access today. 120 of them we can use. So that's 2%. And this is because the metadata is missing on these materials and on their lifetime. What happened to them? How were they processed? What was their state before and at the end? So this is what we want to change, but we want to go further and really introduce how we can put that into a way that we can really earn money with it. So the whole process of preparing the right data is shown in the upper line. So you can see we prepare the samples, we put them into an EBSD, we can find the inner structure with that, then we test them maybe, and we get a lot of information about how these materials behave under the loading conditions. Then we switch into the second line. Because in one sample, and we make maybe 50 or 100 samples with one machine per year, yeah. So that's already pretty fast because we have a high throughput machine. And then the second thing is, how do I analyze quantitatively all these defects growing? And that's where deep learning comes into place, because we can use deep learning to really analyze the microstructure from these images and how it's changing over time. And we connect that and we put this information, what is the state at the beginning, into a computer at the same time. And we use crystal plasticity models. That means that we take a specific site of that inner structure into the computer and calculate how it probably will behave. And in the last point, to be predictive then at the end, we put it into a random forest model and describe then how it will behave at a specific point in time. Now, how does this deep learning work? So we use, for example, a deep learning architecture. It's a UNet shape, it's called. It's coming from biomedical deep learning projects where they found ways to really reduce the information which is stored into into the images and get a specific structure out which is characteristic for what I'm searching for. And this is stored in a statistical way. And then I can extract that again and identify, for example, cracks, or also this roughening at the surface and the pristine surface. And through that, I can automatically process thousands of images now with this technique to really get to see how these materials behave over time. So the next one, if we switch to the second part, the random forest means I have to train all these things. So I bring all that data together and then train a random forest tree so that I can, at the end, predict when I have sensors in my machine, what is the state at the moment, how will it behave in the future, and how long will it last in the future. So maybe I need maintenance, and this is the connection. So if I have this machine connected to an intelligent sensing machine, then I can really predict if I need, for example, advanced predictive maintenance or anything like this. This is the foundation of it. If we come to the end now, what we really want to do with that is to really bring all these points together, and that only works with structured data. So we go from acquiring data, analyzing it, then extracting knowledge, understanding what's necessary behind it, and then go to a state where I can predict what happens in the future, even in a very complicated state as damage propagation in such a material. Last but not least, we don't believe that this will be happening in 1 or 2 years, but this is rather a 10-year or 20-year horizon. But there are many different projects going on the European level, as Gerhard introduced, as well on the let's say, on countryside or state sites. And I'm not going into detail, but if you're interested, you can visit these sites. Thank you very much.
Thank you, Chris. And thanks for going into a little bit of detail, at least when it comes to the fatigue and the fatigue assessment aspects. Now, I've again allotted a few minutes here, but since questions seem to take time before they reach us, it may be a good idea to actually collect the questions rather for the end. I have one question from Gerhard Schumacher to you, Gerhard Schumacher from the project management in Jülich. To you, Chris. I have another question to Gerhard, but we'll postpone that to the end. The question to you is, everybody talks about big data nowadays for advances in modeling and simulation, but how can we ensure that the big data sets do not contain very low quality results? Or results of materials characterization, for example, artifacts in SEM and AFM. How high would be the impact of such low quality information, low quality data on your modeling then?
Yeah, that's a very good question. It drives us around quite a bit because, as I said, the 6,000 data sets, this is almost nothing, right? Big data is definitely a relative description. Yeah. So for Google, big data means a different thing than for me at home. But anyway, the thing is that one data point of these 6,000 costs between 1,000 and 10,000 euros. The second thing is it takes between 3 days and roughly up to 3 months to get one data point. So the 6,000 data points will never grow exponentially, I think, and therefore we will never reach that state where if we have a real machine standing somewhere that we have big data. Nevertheless, the second point you're making is absolutely true. The problem really occurred to us when the 6,000 data points were found. We gave it to the informatics guys, yeah, which really use a lot of or have a lot of understanding of how to use machine learning or AI, and they said, "Oh, only 6,000, but it will work." Yeah, and our problem was then when we looked at them, we found out it was only 2% valid data. Yeah, and if this is true all over the place, I mean, then we will deal with a lot of data which we can probably not correlate relative to each other, and also not bring them to bear for solving a problem here. And that will need two things, I guess, and we're trying to put that into place. The one thing is a curation system, one where we decide as a community what is relevant metadata and how is it acquired. That needs to be somehow discussed within the communities. This, especially, in specific communities. It's not something you can do overarching. Overarching, you can only say we have to do that, yeah? And then every sub-community has to do it. The second thing is, if we are able to really use machine learning or anything like that to really bring that together, then it's probably possible to do that also in an automized way. But that's something we have to see, I guess. Yeah.
Okay, I'll take one more question out of the pool. This is by Alexis Meliziotis from Creative Nano. The question is, what's the difference between the MATLAB process and the forest type processing you showed?
In the MATLAB process, we combine different elements to pre-sort them and do the data fusion on that, and then it's fed into in a structured way into this random forest model.
Okay, thank you. I would like to cut this discussion short here. I store the questions which are still in the questions manager. I hope I can keep them till the end of the session and pick a few others for you, Chris, which are still there. So thank you for at this point, and let's go to the next talk by Giovanni Pizzi on workflows and how data feeds in that. Please.
Thank you very much. So thank you very much. And exactly today I wanted to briefly speak to you about how simulations and digital infrastructures are already today able to accelerate materials discovery, which means also shorten the time to market. So I want to start with an example of some research we did, which is essentially the study of the color of metal alloys, very often precious metals, gold and similar. And what you see here on the top is what the simulation predicted as a color, and the row below is the actual material as a photo of the material after realization, after synthesis. And you see, I think this slide proves you that nowadays simulation, in particular, what we do is we typically focus on atomistic simulations, are nowadays able to be extremely predictive. And this is not a very simple workflow. It involves a lot of different components. It involves knowing how the light hits the material, how the photons excite electrons, and how the plasmas absorb the light, how this in turn reflects into the final optical reflectivity of the material, and how the eye, the human eye, responds to light. And so since we are now able to do this kind of simulations, we actually are changing, revolutionizing completely how materials can be discovered and characterized. We are not anymore bound to discovery in the physical infrastructure of an experimental lab. We can now leverage a completely new concept, which is of digital simulation infrastructures for material simulations. It's really kind of the analog of a laboratory, but in the digital world. And this will allow us essentially to have a representation, a digital twin of our materials in simulations and accelerate discovery. But for such an ambitious goal, we need a kind of advanced technology stack. First of all, we need quantum engines that are able to run this quantum simulation analysis codes. And for this, we use typically density functional theory, which is a theory which has proven to be extremely successful. For instance, if you look at this Nature paper of about 6 years ago, they collected the top 100 most cited papers in the entire scientific literature, not only material science, but everything, medical science, engineering, etc. And out of these 100, 12 of the top 100 were about papers on the methods and applications of DFT, so density functional theory. So nowadays, really, we have a very powerful method, and I showed in my previous slide on the color of metals that this method is really predictive. But on top of this, now we want to predict properties of potentially hundreds of thousands of materials and filter them and screen them to find the best one for a given application. And for this, we need additional tools. And in particular, the tools we've been developing one is called AIDA. It's essentially an operating system, if you want, for high throughput computational science, which essentially allows you to run automatically the hundreds of thousands of simulations you need to run to do real material discovery. And then we want to make all these tools and all this simulation available to everybody, not only in academia, but also in industry, as simulation services. And this is done thanks to our platform, Materials Cloud, which I'm going to mention in a moment. So the first one I mentioned is AIDA, is essentially is a software which allows to simulate, to manage simulation, the high throughput scale. So as a key pillar, which is automation, but also stores the data, as I'm going to show in a moment, in the form of graphs, which I think address one of the questions which was asked before, which is how do we know that the data we produce is high quality? And by keeping the provenance, so the graph, the history of how this data has been generated in a very careful way, but also in a very automated way, because it's very complicated and cannot be done by hand, let's say, anymore. When you have hundreds of thousands of simulations, you can really know the quality of your simulation data. And then this is exposed in an environment which allows to do data analytics and machine learning in a very easy way, thanks to the fact that the data is stored in a database and can be easily queryable. And finally, you can share the results and the data, also thanks to standard protocols and ontologies, as we heard before, are key, as we heard before by Goldbeck and Eberl. So I want to show this in action in a project which was about the computational exfoliation of all known inorganic materials. materials like graphene is the most known, and some materials come in layered form, and it's possible to mechanically exfoliate them to obtain two-dimensional layers. And our goal was, can we predict and create a database which would be the starting point for material discovery of all possible materials that can be exfoliated? And so we implemented a relatively advanced workflow. We're starting from experimental structures. So we want to start by structures, by crystals that exist in nature in 3D form. We want to understand which one were layered, and then we apply a number of simulations in an automated fashion to predict a number of electronic, magnetic, and mechanical properties for a wide variety of applications. Because nowadays, 2D materials are very widely studied because of applications in spintronics, plasmonics, etc. And I'm going to mention this in a moment. And thanks to this, we run simulation for each of these. And unfortunately, the quality here is not very high, but on the left, we have a very advanced graph which reproduces step-by-step the provenance of all the simulations. These graphs are created automatically by AIDA and are stored along with the data. So you don't have only, like in experiments, you don't want to only have the sample, but we have to have an accurate description of the process that brought to it. Here, thanks to AIDA, we automatically store the full provenance of any piece of data we produce, and we can run on hundreds of thousands of materials to predict the best materials. And the result of it is this. So we've managed to publish a database which contains a few thousands materials, and really with this was a starting point for a very large number of material discovery projects, not only on the 2D materials for high electron and high Hall mobility devices, for topological insulators for quantum computing devices, ferromagnetics, superconductivity, transport conductors, etc., but also the three-dimensional parents were key because also they provide very interesting properties, like for ionic conductors in the solid states or for batteries, for instance, catalysts, filters and separation, thermoelectrics, and so on. And thanks to the fact that automatically we store this data, if you want, you can actually give out, in our case, in a fully open science and open access way, but you can give to whoever you want, you are collaborating with, the full data, not only the final result, but the full graph, the full provenance, which essentially is allows you to give a quality measure to your data. And just to make an example, this is not just pure research, because this material, which I'm going to mention, Jacutingate, is a material which came out from our study. And this is a material which was discovered in a mine in Brazil only in 2008, and was discovered by crystallographers and just classified, but nobody knew its properties. And what we did was to discover it has extremely interesting topological properties. It's a K-Milli topological material. And already in the past few years, it has spurred a lot of interest and a lot of studies to understand its physical properties to then be applied to real devices. And finally, once we have these tools, we don't want to make these tools available only to academia, but we really want to make them as services available to anybody, also especially in industry, to push for materials application in real devices. And this happens in what we call the Materials Cloud, is our web portal for moving, if one would say, moving the science to the cloud, and in particular one platform, which is the AIDA Lab, which is a way to run reproducible simulations with the full provenance in a way which is accessible to everybody. Now, in the next slide, this was supposed to be a video. I'm not sure this is going to play or not. There were some technical issues, but essentially I wanted just to tell a brief story before concluding, which is the story of a laboratory. It's called EMPA in Switzerland, where they do both simulations and experiments in the same lab. And AIDA Lab has allowed them to really speed up by orders of magnitude the feedback between experiments and simulations, where the experiments and the experimentalists and the theoreticians can sit together at the same table, look at experimental results, quickly run new simulation, which trigger very complex workflows. And the next day, they have the results and they can compare and decide how to improve the experiment. And sorry that this video, unfortunately, couldn't work. But the message here is, as we know, materials enable the technologies that now power our economy, our lives, and our society. And we are nowadays able to change the entire paradigm of design and discovery thanks to the fact that first principle simulations are able to predict novel materials and devices. And thanks to this, we are now able to implement and put in production open digital infrastructures that allows to do world-class science in a way which is available to all. And with this, I would like to conclude, thanking all the support and acknowledgements of not only the academic funding we have had in the past years that support all our research and development, but also our industrial partners that you see listed here. Thank you very much.
Thank you very much. So again, I'd like to invite the audience to raise questions if there are. Until then, Giovanni, maybe one from me. How do you rate the importance of bringing actually the experiments and the modeling together? I know you come from a purely DFT modeling background, and so maybe you can spend a word on how this interaction, what kind of challenges this interaction poses.
Sure, no, that's an excellent question. I think it's key. It's very important to be able to merge the two, because if you do only simulation, you have no way to verify what you did works. It's not really going to produce real results and real materials you can put in the market. For us, really the experience we had for instance, in the lab I was mentioning before was that the time, often the experimentalists would come with their image from the laboratory, and they would ask the experimentalist, okay, can you explain, help me understand what this is about? And in order to speed up the process, now with our infrastructure, the goal is really in a day, you can run a new simulation, which often requires tens of steps, and come out with a result and compare with the experiment, and the two can sit down together at the same table and decide what the next step. And so you go down from weeks to decide what to do next to days, and you can really speed up the process, and you can combine the strength of experiments and theory, because very often experiments can measure easily certain properties which are hard to simulate, and simulation can simulate very easily and accurately other properties which are hard to measure experimentally, and you can put them together.
Yes, that is certainly one of the key challenges. Thank you very much. And with that, I'd like to call for the last speaker, Mr. Bernhard von Vacano from BASF will certainly give us a view into the usage of the data and the application side. Please.
Thank you very much, and thanks for the opportunity to add an industrial perspective to what we've heard before. And you will see that a lot of the things that are coming out of academia and this consortial work that has been mentioned is already finding applications. And to do that, I want to take you through some examples. They are all embedded in what we as a company need to do. We want to create chemistry for a sustainable future. And BASF, as a leading global chemical company, we are serving a lot of industries. So you will find very few products that in the end you as a consumer would buy that have a BASF label on it, but you will find a lot of our materials, chemistries, and solutions in the cars you drive, in the products you use, in the shampoo you used this morning. And that said, we see a big need, but also a big opportunity to really drive sustainability through chemistry. And that said, that requires a lot of efforts in research and development. And research and development in the material space, as has been mentioned before, typically suffer from very long timescales to get everything right, to go through a typically trial and error process in the lab, and then identify good candidates for, and then figuring out how to make them at scale. And this can take easily several years, up to 10 years, depending on how complex the question is. So what could change this kind of paradigm of how materials R&D is done? And the big driver we see is digital tools coming up, and digital tools really revolutionizing the way also industrial research and development is done. So we think that while the innovation landscape as a whole is accelerating with the number of scientists increasing, the number of interdisciplinary fields increasing, patents and literature numbers exploding, there is one thing that can help you to both speed up and also be more efficient in this experimental process is to really leverage digital technologies at all levels of this innovation chain, if you want. It starts with the lab. It starts with making your lab digital, capturing all the data, as has been mentioned before, in the right context, introducing electronic lab notebooks, connecting all the devices, testing experiments, synthesis, apparatuses, so that you store all the data also about the processes, how materials were made. Then, of course, you have to handle the data. You have to create knowledge from data, which has also been referred to before. You need structures, how to do that, and you need to be able to derive decisions out of the data. And BASF has really embraced this specifically in R&D, with founding a specific department that is driving digitalization of R&D with 200 computational scientists, modelers, statisticians. We have invested in a supercomputer capability, so because we also see that the need for the computational infrastructure to be there to do more with modeling. And also we realize that we need to partner with external partners, other institutes, academia, but also our customers, for example, to drive this field forward. I decided to give you 3 examples that go along this chain, starting typically from experiments in the lab, touching production, assembly, and finally the use. And the big challenge, as I've mentioned, is really reducing the impact that we have on our planet. So driving sustainability, meaning reducing emissions, meaning reducing harmful impact on people and the environment, but also, and this is something that comes back to what was mentioned by Chris Eberl, really taking a cradle-to-cradle approach and understanding how materials can also be designed in a way that they can be fed back and create a circular economy. The first example is based, and that would have been a video that showed you how a high-performance computer simulation shows what's happening in your washing machine. So in this case, we take all the information about the ingredients in the laundry detergent, the surfactants, some additives, polymers, but also the grease, the textile, everything together to recreate the processes in the washing machine. So you can really, on a molecular level, understand what different ingredients do. And the aim is to boost the performance at low washing temperatures and reduce the amount of surfactants needed, because that has a direct impact on the CO2 footprint. And heating up water is sort of the most energy intense process in your laundry. So this brings everything together using modeling, high performance computing, and information about a process that is in the end happening at your place in the consumer. The next example touches upon materials and how we start not only selling materials as a physical quantity, but the materials plus their digital information and sort of a digital added value. Because what we do is we take all the materials from all the information about how the material is composed and how it was made, what properties it has, together with how it can be processed. So for polymers, in this case, engineering plastics, we can predict how a specific part that was only computationally be designed can be made, how the performance of the polymer will be, and we can even then do test the part without ever having made it. So and we can provide this information about our materials, how they're being processed, to our customers, which would then take such a part and maybe use it to lightweight their electric car. This is one example where we already take the next step and also try to link it to a digitally enabled material business model. And then finally, what happens at end of life? I picked 2 recent examples where we also really try to attach the right data that you need to a material to make the right decisions for recycling, but also for designing sustainable applications. One of them is to combine physical tracer technologies and digital tracing of materials along the value chain. So we make a material, somebody else makes a part that is being assembled in a car. The car is going to be repaired, and at the end of life, you want to know what kind of material did you have and who is taking it back. And this can be done by putting in physical tracers, so a molecular barcode if you want, combined with representing that part and all the history, maybe on a blockchain. This is one of the pilot projects we are running actually in Canada right now. And then the other thing we are doing right now is to attach all the information we have about the history of a product and how it has been made and how it has been processed with regard to their CO2 emissions. So we now have a digital model that allows us for all of our products and all the intermediates to come up with the information about the CO2 footprint, which is also something our customers can use to make decisions on which materials to use and if they have choices between different alternatives, for example. So these are all examples how to really to see the R&D value chain being transformed by digital technologies, and the foundation is that we have the right information that we need and that we can, from one scale, also coming back to this multi-scale approach, from the molecular scale to the processing, that we can transfer the relevant information and at the end also understand, like we've seen in the last talk, where the information has come from and that we can trust it and that we can build on it to come up with new solutions. So data integration is key. And as I've said, we'll also have to come up with ways of sharing data along the value chain, finding the right standards, how we can communicate with our customers and their customers, and then finally recyclers maybe to really leverage the potential of a digital twin of materials. And with that, I'm at the end, and I'm happy to take any questions now or later.
Many thanks, Mr. von Vacano. This was truly inspiring, I'm sure. And I'd like to call again for questions in the Q&A session. Please don't hesitate to put in questions also to other speakers, which we've heard already. And before I see anything here, I'll bridge the time maybe myself again with a question to you, Mr. Vacano. You have nicely emphasized exactly this aspect of combining modeling simulation with the experiments from an industrial perspective. You've also mentioned that you are selling the data together with a product or give it together with a product as a part of the value of the product. Yeah. Now, to which extent do you consider you need to know what the customer of your product wants to do with it in order to assess what he needs as data? So I'm sure you will have to prepare modeling in this respect so that your customer can actually use the data in the appropriate way. It's not, yeah. Maybe that's one aspect that you could focus on.
Yes, true. And that's one reason why you want to have a reusable data infrastructure and models that can be reused and adapted. Oftentimes, if you know the industry, you know what kind of physical application tests, for example, customers are asking for. So you try to mimic them digitally. But of course, you should be able also, if they come up with something new, to quickly find a way of digitally representing it.
So, sorry to recast on that. Do you consider this a classical back and forth process, or to which extent do you actually prepare for the questions your customers may have?
It starts sort of out of the traditional back and forth, the customer-supplier relationship, but I think we need to go beyond that. And also understand our customer's customer and what I talked about, circular economy questions, what is happening at the end of life and how is it coming back? And we might have another role when it comes back, so we might be in that chain twice. Yeah. So definitely.
Okay, so thank you very much. And I'll pick again one question out of the pool which was raised to Gerhard Goldbeck by Beatriz González Caballero. Do you think in the future modeling would or could replace traditional testing? Gerhard,
oh, please. Not at all. Not at all. So It's definitely very much complementary, as we have already heard. And I think one thing I would like to emphasize here is not just the complementary nature. There is an element of creating data from modeling. We've heard from Chris as well that it is very hard sometimes to create substantial amounts of data from experiments. So they're very, very precious. But digital technologies need a lot of data. So while it's not a replacement, it's certainly from the order of magnitude perspective, we should aim for creating a lot of valuable data, and thereby, making the most of the really treasured measurements and high quality experimental data that we have.
Thank you very much. Good. I'll take one more question from the pool, and please don't hesitate to put further questions in which are more general, maybe also address the speakers as a whole, not just individual questions. I'm getting a strange background. Sorry. Okay, so one more question is by Dietmar Hömberg from VIAS. I think this was mostly to you, Chris, but maybe the others would also want to give their take on the question. It's regarding predictability. There has to be a difference in behavior depending on the actual structure and its loading history. How can you account for that? How would you account for that? Chris, your microphone is off.
I'm sorry. We have definitely protocols for that already. And the main thing is really covering this high-dimensional space as you describe it. So if you have a different bunch of loads which you apply instead of always the same cycle like we often do in experiments, the question is how can you map that realistic behavior onto something you know? And that requires a lot of understanding of the underlying mechanisms. And I think this is where we come back to what Bernhard and also Giovanni showed. This very tight integration between simulation and experiment allows you to find the sensitivities. And therefore, we can kind of predict how that works and use, let's say, in this high-dimensional space, on one hand side, data points as clusters, as well as physical modeling to really describe the shape of where that lifetime lies. Yeah.
Okay, thanks. I do get background questions whether we could end at 12. I have 12:20 as the end. Okay, so unfortunately, I have to cut the session short. I was expecting to have 10-15 more minutes for discussions, but that doesn't seem to be the case. So let me wrap up quickly and excuse the questionnaires that I haven't gone through all of them. We have had very interesting contributions on various aspects of data usage. We have looked in detail at the interface between experimental data and modeling and simulation, which is certainly one of the big challenges, but also one of the aspects where most potential can be seen in for future activities. Thank you very much.